Today we're going to talk about simulating control systems in GoldSim, and we're going to focus on three different types of control systems. The first one is an on-off that we'll look at. The next one is proportional, and then finally we'll look at PID. And I'll talk about the third one a bit more if that's new. But first, before even getting into on-off control, I want to talk about the type of, I think we could call it control, that we see a lot of users going toward, and this has some problems. And so I'll show you what the model's doing, and then describe how this can be problematic. Sometimes it causes oscillations and other problems in the model that eventually cause the runtime to increase so much that eventually somebody comes to us with a question asking what's wrong with the model, and this is often what the problem is. So what I'll do is describe first the model, and every example that I'll be showing you today runs off of this same exact type of application. What we're looking at here is a tank that's a cylinder shape, and it's got some volume of water, and over time we are drawing water away from this tank just using some sort of demand value that will start with a constant, and then I'll show you with random numbers that we'll be applying to that. As water is drawn from this tank, then we calculate the water level using the height and the radius of the cylinder. So it's pretty simple. This water level is something that we're keeping our eye on here because we want to maintain that water level to some target that we've specified, and the target level is shown over here. It turns out that I have a moving target. It's a target that steps down. If I plot the target, you'll see it looks like this. It starts out at 2.5 meters, and then over the course of the day we drop it to 2 meters, just to show you that we have a dynamic target. Okay, so what we want to do is we want to pump water into the tank at a rate that tries to match that target level. That's the goal, what we're trying to do here. And so what we see a lot is somebody putting in a switch element, or what we call a selector here, and they'll say something like this: if the current water level is less than the target, then pump some water into the tank. Otherwise, don't do anything and just let it draw down based on the water demand. And it could be the inverse of this, where you might be turning a pump on to draw water away from it, and you have uncontrolled inflows coming in. Otherwise, it's the same concept. You would just flip around the conditional statement here and say it would be greater than instead of less than, but it's essentially the same thing. So this might be what you'd think is the most straightforward answer to this. And if I go to a plot, let's see, I built a little dashboard here for this. If you look at a plot of the water level compared to the target, which is shown in the lower plot here. By the way, if anyone's having any trouble seeing this, please do let me know. I tried to make the resolution such that it would be somewhat easier for most people in the audience to see. But you'll see that the red line shows the target down here, and the blue line is the current water level simulated in the tank. And you can see that we start out lower, so we're pumping water into the tank, and it hits the target, so we stop, and then it drops down a little bit, and then it turns on, and so it's essentially turning on and off. The problem with this logic using the selector element, it is very dependent on the time step, and that's the only reason why this water level is dropping below the target as much as it is because it's just waiting for the next time step to occur before it figures out what it needs to do next. So for example, we could lengthen the time step here. If I go to the simulation settings and make this time step larger, now if I run the model, you should see that it will drop down and or rise above the target even more than it did before, based on the time step. So you can see it's very sensitive to the time step. And what you might think here is, well, I want to hold a water level very close to the target, so I'm going to make my time step very small. And if we do that, let's say I make the time step much smaller, 10 times smaller, what happens here is you get rapid oscillations of the inflow here that's essentially coming from the controller. And if you, in the real world, if you had a pump that was turning on and off to maintain this water level, you would very quickly burn the pump motor out, requiring it to turn on and off so many times during the day. So this is not a very robust control system here. What we want to do is we need to provide some memory to the state of the system, and also provide a buffer around the target. If you operate a thermostat in your house to manage a temperature, the temperature is going to fluctuate around a target in your thermostat before a furnace turns on or off to manage the temperature. That's the same type of controller that we're going to use in the next example that I'll show you. So the switch element, you can see it works. It's able to maintain this water level to the target, but it's not working well. It's causing problems with the equipment. But in the model, as far as the model goes, this causes a lot of oscillations, and that could cause problems downstream in your model if you're doing calculations that are a function of this inflow. So and another additional problem to this is if your target happens to be at the bound of, like the upper bound of the reservoir or pond, that hitting that bound causes an unscheduled event to occur, and that could insert unscheduled events and even further shorten your time step dynamically. That can cause a lot of problems in your model. So I would suggest staying away from this type of control logic to control water levels in a pond or tank. Okay, and I know that it says PID controller. That's because I copied it over, so you can ignore that. This is just a kind of a quick example that I did. Okay, so the next one I'm going to show you now is similar, but it is using some control logic that provides a way to be somewhat independent of the time step. And what we have here is a basic on-off controller that works like a thermostat would work in your home. What this does is it says, okay, I'm looking at my target, and I also have a sensor in the tank. And this sensor is reading the value of our water level, and it compares that to the target, and it says, here's my error that I have. This is how far away I am. And with an on-off controller, it doesn't really matter the magnitude of the error. All it needs to know is, are we outside of the range of target or not? And in our case, we have a range. We have an upper and a lower limit above the target. And you can see that in the lower chart down here, where there are 3 red lines. The lower one is the lower target. That's the point at which we say, okay, we need to shut off the inflow. But it allows us to draw down below the actual target slightly before we turn the pump back on. And then when it turns on, we don't shut it off until it rises above the upper limit. And this buffer allows you to it provides a way to turn on and off a pump without burning it out, or a motor, or whatever it is that you're operating here. And so we could, in this case, we could change the time step, which I'll do now. I'll make it a very small time step and run the model. And now you see we're not oscillating like we were before. So this is definitely a success here. You can see that we haven't changed very much in the way that we're operating around that target. It's still oscillating about the same as it was before, and we're also not oscillating as rapidly. In fact, in the other example, we were oscillating about once a minute. So now we're only doing it about twice an hour or something like that. Okay, so this is a really good way to keep your control independent of the time step. So it's a very practical and simplistic way to control. So if I go into the model, let me show you how this is working. So you can see the model looks very similar. We have still the same target, and we have a selector, still using a selector to determine whether we have water flow into the tank or not. And it's just an on-off. It's a binary. It's either on or off at some given flow rate that we specify. So it's very simple. We don't have any kind of throttling or anything like that, just on or off. But the key point here is how and when we determine when it's on and off. And what we're doing is we're looking at this conditional output right here called on-off. That is coming from this script element right here. And the script element has the logic for the OnOff controller. I used a script element just because it's a little bit more compact. You could do this very easily with just basic GoldSim elements. One of the key elements being the status element is what you would use, and we do have an example in our library that does it that way if you'd like to see it. But I put it all in here just because it makes it all pretty compact, and all you really need to do is just provide the inputs of the current water level, what you're sensing from the sensor, and then the target level and your deadband. And just to review, the deadband is this range between the upper limit and the lower limit around the target. And so in a model, for example, you could say, well, maybe I'm okay with a slightly larger deadband. So you come in here and say, let's make it 0.25 meters and rerun the model. And what you'll see is that the pump will oscillate on and off less. And because we're allowing the water level to rise above and below at a larger span than we did before. Okay, so in this script element, we don't need to go through each line here, but the important part is that what we say is we have we're looking at comparing the target to or not the target, but the actual the value of the water level plus the half of the deadband, and that's where we say we're allowing it to rise above the current water level by half of that span, and if that happens, then we're going to turn off the inflow. Okay, and so that's where we come down here where it says update the status controller, and this is similar to what you would do in a status element. You would trigger it to be true if the measured value is less than the lower limit. It turns out that you only want that to happen if it's currently on its way up. And then you would also look at, is the measurement greater than the upper limit? And in that case, you'd want to make sure that you're currently on your way down. And if those conditions are true, then you would turn the pump on. And so you can, when you look at this model, you can see how this is working. But essentially, what you end up with now is an output called on/off, either true or false, and that will then control the flow going into the tank. Okay, so what happens now if we add some uncertainty to this model? Right now we're saying there's a constant demand of 0.5 cubic meters per second. And that's why you can see that the pump is oscillating approximately on a regular interval here at 1 cubic meter per second. In fact, if we made this closer to 0.5, then it wouldn't oscillate much at all. Okay, but let's add some uncertainty to the discharge and see how we react. So I'm just going to change the model to probabilistic and run a single realization here. Now I'll run the model. And you can see that the way that the inflow pump is oscillating is now different, and that's just because the demand is now, there's some uncertainty in the demand. And you can see how we're not staying to the target very well here, because one of the reasons being that we don't have a lot of capacity in the pump. We turn the pump on for 1 cubic meter per second, but the demand at this point must be much greater than that, and so we draw the pump down, or the tank is drawing down here. So let's try rerunning this with a higher capacity pump, let's say 2. And now you can see we are able now to stay a little closer to the target. In these cases, there's just that one spot where we can't. But this is doing pretty well, I would say. Okay, so this is the OnOff controller. Let's now look at another controller. Let's look at the let's go ahead and just look at the PID controller. So I'm going to go to that model now. Okay, so the PID controller has 3 components within the controller itself. It has a proportional function, integral function, and derivative. We can go in and we can look at each of those if you go into this PID controller container, and it walks through and describes what each of these terms are. And you can look at the calculations themselves. Essentially, they're all based on some sort of error that we come up with. The error is a function of the target compared to the current measured value that we're reading, in our case, the tank level. Now keep in mind that all of this can be done for other types of systems. It doesn't have to be a tank of water. It could be, like I was showing you earlier, the temperature in the room, or any kind of system that that you might be modeling in which you have to control a signal that changes that system. So we look at this error, and in this case we need to see 2 kinds of errors. We need the error itself, and then also the derivative error. And the derivative error, if you look at that, it's, well, first let me show you the error. The error itself is just the calculated value. This is the measured water level minus the target level. So it's just the difference between those two. That's it. That's what it's always been, actually, in the other examples. Then to get the derivative error, we say, well, what is the change of error over the last time step divided by the time step length is all that is. And then that error is used for the derivative output. But for the proportional output, all we do is we take the instantaneous error, what's the error right now, and we apply a factor to it called the proportional gain constant. The higher that number is, the faster we respond to the error. But also could be a cause of oscillations, so you don't want to make that too high. The next one is the integral error, and the integral error is really just the integration of the error. So you just take that error and you divide it by the time step and you integrate it. And that integral error is what we use to provide the integral output. And this is what kind of provides a kind of a systematic correction over the duration of the model. And we can look at each of these and how they compare over time by just running the model. Let me run this model deterministically. Okay, there we go. It's already deterministic. We run the model, and now if we look at the individual errors, move this plot up here, then you can see how they're different. So just the instantaneous error is shown here in red. This is how much we're off from the target over time, and then the integral error. This is how much the cumulative error is off. and then there's the derivative error there. So we use a combination of all three of these multiplied by a coefficient. And these coefficients can be changed. And that's how you tune the controller, is by adjusting these three coefficients: the proportional gain constant, the integral gain constant, and the derivative gain constant. So you multiply those by those errors, and you sum them up and come up with an overall controller output to then drive what the flow is going to do to get it back to the target. In other words, reducing the error is the goal in this model. So as you can see with this model, the top chart is showing us the various controller outputs, and you can see here that in this particular case, the proportional output is being used the least. It's just for when the error is the greatest, and then we're relying more on the integral correction, and very little on the derivative. But that just so happens to be due to the fact of this, the particular model that we're running. But you could adjust these gain constants to to adjust how that's reacting. But you don't want to adjust these numbers much more than what we're showing here. Okay, so this is how it operates under very steady conditions where the outflow is constant. But let's change the model so that we have some variation in there. So I'm going back to edit mode, simulation settings, Monte Carlo, and now I'll change this to probabilistic and run a single realization box and run the model. And now you can see that because of fluctuations in the demand, we have a reduction in demand, so we've overshot the target and come up pretty high. This is not really something that can be controlled once you're above the target. We have to wait for it to draw down through the demands, because we cannot control the demands in this case. So you have to just essentially wait, and that's why all of the outputs from the controller are essentially zero during that time. Then we drop below the target. You can see something rises above. In this case, is the proportional, and so on. What the integral and the derivative outputs are allowing us here is it's providing a way to prevent oscillations, and it does a pretty good job of getting us back to the target with minimal amount of trouble here. The nice thing about this is that we don't necessarily need to know what the demand is. We just need to be able to provide enough inflow capacity that we can meet all of our demands, but eventually we're going to get back to the target. So it's a pretty robust controller type. All right, the next one I want to show you is one that's a bit more simple than this. It's called the proportional controller, and so it doesn't require the integration or the derivative portion of it. So let me go to that model. I'm going to keep this one open in case we need to compare. Let's see here. So this one open. Okay, so the proportional, what it does, if I go in there, it just has these two outputs. So again, we calculate the error, and we also, in this case, we have this proportional output that it's calculating. Essentially what it's doing is combining two things. We take the error and we multiply that again by the proportional gain constant. But in addition to that, we want to take what's called a controller bias, and the controller bias is based on the average outflow. And if, let's say, the average outflow is 0.5 cubic meters per second, then we'd want our controller bias to be 0.5 cubic meters per second. But you may not know ahead of time what this average outflow is, so it would be difficult to to say this is what the controller bias is. If that's the case, one thing you could do is you could calculate the controller bias by simply determining the running average of the outflow, which is what I've done here. So if I do a function of on this element here, function of, you can see that it's a function of this thing called cumulative demand. All I've done is I've taken this demand, which could be random, and I said I want to know, first of all, calculate the cumulative value of it, and then I want to know the running average over the entire simulation. So I'm going to calculate the average over the averaging period of the entire simulation. So I just put sim duration. That's a run property in GoldSim, which makes it easy. I can run this for any duration, and it would always calculate the average over the entire simulation duration. So now by doing that, I don't have to input the average demand over time. I can simply just read the running average and have that input. So that means with this method, I only need one input. I just need the gain constant. So with that, all we need to do is say what's the inflow capacity and what is this gain constant, and run the model. And so you can see in this case, we don't have the oscillations that we had in the first two examples that I showed you. And it looks like perhaps we have a question. Nope, no questions. Okay. So this proportional method, you can see it draws pretty quickly to the target and gets exactly on the target, stays there. There is no oscillating here, but this can get a little bit out of control once we start putting in some uncertainty in the demand. So let me go ahead and do that. Change this to Monte Carlo probabilistic, run a single realization, and run it. Okay, so now you can see that we're fairly consistently above the target. So we'd probably want to look at changing our inflow capacity a bit, but you can see here that we might be messing around with our constants here a bit in order to get to the target a bit faster. And so it's not quite as robust as the PID method that we saw earlier. This also could be due to the fact that the bias factor that we put in here is overly biased by initially having some low inflows, and therefore causing this to overreact. But eventually, if we ran this for a long enough of a duration, it might settle down a bit more. If we went in here and we said, well, I'm just going to force force the bias factor. Let me try that now. So I'll change this to just be a constant 0.5. Change that. So now we're pointing to just a constant. Run that. You can see that it's a little better. We are staying a bit closer. It came down, and now it is a bit closer to our target, but it's still having some trouble. We can try to change the gain constant to get it to react a bit faster. So we can change this to 4 and rerun it, and you can see that it's a little bit better here. All that did by changing that gain constant, it made it increased the amount that, or it increased the sensitivity to the error, I guess we should say, which causes the flows to increase, the inflows to increase during periods when we're not close to the target. And so that would cause you to more rapidly get back to the target again. So you can see how the proportional controller is quite simple and quite robust, but you need to know something about the demand, or we should say the external influences on the system. We need to know a little bit about that ahead of time before we can get this controller to work very well. So that would probably be, so the benefit here of this one is that it is a bit simpler, and under some cases it can perform quite well, but in other cases it may not if you don't know much about the influences on the system. So those are the three different types of controls that you can implement in GoldSim. And there are others that we've not implemented. There are lots of different ways of implementing various control systems. But as you can see, the three that we looked at are a really good alternative to what we see a lot of people using, which is just a simple if statement. And by using these, you can get a lot of benefit in your models. And I know that what I'm showing here is a very short time step, but these controllers can and do work under situations where you might have even a one-day time step over a long period of time. What's important is the amount of storage that you have versus the amount of flow going in and out of the storage. If you have a small amount of storage and a high flow, then you would need a smaller time step to use these types of controllers. So that concludes the presentation. I'm happy to wait around a bit to see if any of you have questions and answer them. So feel free to ask any, and thanks a lot for joining us today.